and now we're going, the end of last video, we ended up with the stiffness matrix for the reduced integration, and now we're going to do the force vector. And as I stated in the description, the force vector is just omega squared times xy, so there's an x and a y component, and the x component is just proportional to x, and the y component is just proportional to y. And what we need to do is we need to integrate shape functions times this vector, right? And then this is going to be, this FEB is going to be an 8x1 vector. So it's going to have 8 entries because it's going to have the N1 times the BX, so the X component of the body force, N1 times BY, N2 times BX, N2 times BY, and so on. So there's 8 components. And again, in the homework 6, you will actually have to do a loop over integration points. I don't have that. I'm doing the reduced integration. So if you have reduced integration, so if I had a loop, I would have this plus equal weight times the determinant of Jacobian times the function that I need to integrate. But I'm doing single point integration, so I'm going to do just a single weight. So I don't need a plus equal, just FE0 equals weight times the determinant of the Jacobian times the function that I need to integrate. And as I said, this is n times b, where the first entry is n1, so I need to integrate the first shape function times the x component of the body force vector. So the body force is just omega squared times xy, the x component is omega squared x. So here I just have omega squared times x. The x is the one that corresponds to this psi and eta. Then the next entry is again going to be the weight of the integration point times the determinant times the n1 again, but now with the y component of the body force. So you can see that the first 2 entries correspond to n1, and just the difference is that is the x component of the body force and the y component of the body force. And in this case, it just so happens that the x component of the body force is omega square x, and the y component of the body force is omega square y. This could be different for a different body force. So this thing that is highlighted now, that's just the y component of the body force. You can imagine that if you had gravity, for example, you wouldn't have omega square x. You would have, for example, 0 in x, and you would have, gravity times density in y. So yeah, so this is just because for this problem, this is the x component of the body force and this is the y component of the body force. So next 2 entries correspond to the second shape function. So you can imagine that this is going to be now weight times determinant times the next shape function times the x component of the body force, and then the integral of second shape function times the y component of the body force. And you can see the pattern here. Just gonna copy everyone. So n1 n1, n2 n2, n3 n3, n4 n4, omega square x, omega square y, omega square x, omega square y, omega square x, omega square y, omega square x, omega square y. So hopefully it's clear that I'm integrating each shape function times the x component of the body force, and then each shape function times the y component. Alright, so now I need to do the assembly. In this case, the stiffness matrix, for example, is an 8x8 matrix. So if you want to do the assembly by hand, line by line, you will need all 64 entries, and that's not very convenient. So instead, what I'm going to do is I'm going to have a couple of loops. And this, I did it for lecture 24, so also check that out. But it's convenient to put as I was saying before, it's convenient to put all the nodes, this node 1, node 2, node 3, node 4, into a single node map vector. And then what I can do is I can loop over and then get that node. So what I'm gonna do, let me just do the assemble of the K first. So now I'm gonna have two loops over the nodes. I can do better than that. I can actually have a loop over coordinates. And this is because now I want to loop xy, right? So then I have this for core j in range 2. So what this is doing is I will loop to go over each one of these nodes. I will loop xy then again loop over the nodes, and then loop over the coordinates. And then you'll see that the entries that I need are let me just do the first index, or the row basically for the, let me just say, the row of the K matrix that I need to access is going to be the number of the Ni, right, times 2 plus core I. So that this will now go to the from 0 to 8. And then in call is going to be nj times 2 plus core j. So now in row and in call, they are gonna go from 0 to 8, because for example ni goes from 0 to 3. So when this is 0, and then I can get either 0 or 1 depending on whether core I is in a loop also, and that takes the values 0 or 1. So for ni equals 0, I will get either 0 or 1 because of core I. Then for ni equals 1, now I'll get 1 times 2, that's 2, plus 0, that will be 2, or plus 1, that will be 3. So that I have covered 0, 1, 2, 3. And then for ni equals 2, I will cover 4, 5. And then for ni equals 3, I will cover 6, 7. So I will go from 0 to 7. And then the same, but for in call. So you can see here, this is gonna basically go through every possible entry in the KE matrix. So all 64 combinations are gonna be covered because of these for loops and this way of building this index for the row and index for the column. Now in row and in call will cover all 64 entries of KE. And then the thing that I need to know is where this goes into the K matrix. And it's actually very similar to this. Maybe I should have said this is in KE, so the local index. And now I need to know, so where does this go in the global K? And that just means where does the Ni go into the K. And so that would be, let me just copy this again because this is actually very simple. So instead of Ni, node Ni goes to global node 1 or node 2 or node 3 or node 4. Actually it goes to basically node map Ni. So when Ni equals 0, that means that the local node 0 goes to node 1. When Ni equals 1, that means that the local node is the node 2, global node 2, and so on. So yeah, that's all I need. Node map. I basically just need to go from local node number to global node number. So that's why I need this node map. And that's it. So this is and k row and k column. And so that should take care of the assembly of the stiffness matrix. And then if I want to do the assembly of the force vector, now I only need these two loops, and then I need the same, but let me just do index FE. I don't have columns, really, I only have a single row. And then here I'll have index F, that's just node map. And then I have F of int F row plus equals FE of int FE row. That's about it. Hopefully I didn't make any mistake. I did make a mistake. I should name it core I. Yep, okay, so this should work. So at this point I have the global stiffness matrix and the global force vector already assembled. That's all I need. I don't really have any forces. I can just do the partition. To do the partition, I need to identify the nodes that have essential boundary condition. I have ordered them, so if you loop through every node, you can check whether a node is on the, shouldn't say on the top or node boundary, it should say, so check how many nodes are in the inner boundary. For example, I start my count at 0, I loop over the nodes, and then I'm gonna check if this equation of the circle is satisfied. Then I'm gonna add to my count, and then I'm gonna print my count at the end. Node IX, this should just be, sorry, I'm skipping this. So node IX equals node XI. So there's 64 nodes that are on the inner boundary. They are ordered. I already ordered the mesh for you, such that if a node is on the inner circle, it will be one of the first 64 nodes. And then you can partition. So because they are in order already, you can partition. So this is going to be 64 times 2. I feel like I made some mistake. Is it really 64? Well, I guess it is. And this is 2 times the number of nodes minus NE. Let me just check that it was 64. Yep, it is 64. Okay. Yeah, so 64 nodes are in the inner boundary. So the NE is twice that because of the X and Y constraint. And NF is the total number of degrees of freedom minus the essential boundary conditions. Partition, same as usual, so no need to worry there. I need to fill in the vector with the essential boundary conditions. In this case, I have just fixed boundary conditions, so I don't need to do anything, just create a vector of zeros of, yeah, NE. So I'm using count here, but maybe it's clearer if I just say NE. And then, yeah, solve as usual, nothing special. Assemble everything into a single vector. So basically, U will have DE at the beginning, followed by DF. Because remember, DF is not the size of the total number of nodes. It's just the free nodes, whereas DE is the essential boundary conditions. So I can put them all together into a single vector. And then U is just reshaping that such that I have two columns, one for X, one for Y. But it's just, yeah, reshaping the D vector. And then I can plot it. For example, I can plot the magnitude of the displacement. So again, just for the plotting, loop over the elements, get the nodal coordinates, define the polygon, and then what I do is I color each quadrilateral by the average of the magnitude of the displacements. So you can see that this square root of un10 square plus un11 square, that would mean, so displacement of node 1 component x square plus displacement of node 1 component 1 square root, that would be the magnitude of the displacement of node 1. Then this is the magnitude of the displacement of node 2, the magnitude of the displacement of node 3, and the magnitude of the displacement of node 4. And I just take the average of that. So then the color of each quadrilateral is the average magnitude of the displacement for the quadrilateral. And that's it. And you can see that, obviously there's zero displacement here at the boundary, and then as you go away, you get more and more displacement, still pretty small. But that's it. That's a problem of linear elasticity with quadrilateral elements. Yeah, see you on Monday.